work with Doni Kasioki. So we'll first describe the kind of structures we are interested in. And then after we have described the structures, then we'll see what to count. So a tree is a connected acyclic graph, simple graph. Simple in the sense that there are no loops and there are no multiple edges. And acyclic means that there are no cycles. And connected, it means that you can always get a path between any two vertices. And some of the examples of trees include uncrossing trees. Then there are plane trees, DRE trees, among others. So here are some of the examples of trees. We have Cayley trees. These are just labeled trees. Non-crossing trees, these are trees drawn in the plane such that the vertices are on the boundary of a circle, and edges are line segments that do not cross inside the circle. And then we have plane trees. These are trees in which position of a vertex is important. So we know that Cayley trees on n vertices is counted by the Cayley's formula, that is n raised to power n minus 2, and the non-crossing trees on n vertices is given by a generalized form of Catalan numbers, while plane trees is given by Catalan numbers. And one of the important properties of trees is that between any two vertices, you can always get a unique path between them. So a vertex I in a plane tree is said to be at level 0 if there are L edges on that path to the root. And by that sense, the root is at level 0. And a vertex V is said to be a parent of a vertex. A vertex V is said to be a parent of a vertex U if they are adjacent, but U is at a higher level, while it's a child if it is at a lower level. And the number of children at a given vertex is its out degree, and therefore a vertex of out degree 0 will always be referred as a leaf, and a non-leaf is always referred to as an internal vertex. And the degree of a vertex, this is just the number of vertices that are adjacent to it. And in plane trees, the out degree and the degree of a root vertex therefore coincide. And we also have out degree sequence, which is an arrangement of out degrees, and the degree sequence is just an arrangement of degrees of vertices in the tree. And a collection of trees is referred to as a forest. So plane trees have been enumerated according to number of vertices. Then we have leaves, degree sequences, out degree sequences, forests, among other parameters. So as for a non-crossing tree, just like plane trees, a degree of a vertex is the number of edges which are incident to it, and a vertex of degree 1 is said to be an endpoint. So we can also talk of ascent edges and descents. So an ascent edge, so if ij is an edge, and I is the one that is closer to the root, and it happens that I is less than j, that's the j has a higher label, then that edge is said to be an ascent. Otherwise, it is a descent. And an uncrossing tree is said to be increasing if there are no descents in the tree. And for the boundary edges, these are the vertices of the form, or the edges of the form I plus 1, or 1 n. So non-crossing trees have also been enumerated according to a number of parameters. These include vertices, leaves, out degree sequences, forests, descents, boundary edges, maximum degree, among other statistics. So the question, therefore, is can we find a common way of unifying these results for the plane trees and non-crossing trees? So one common technique that has been used in the enumeration of non-crossing trees was introduced by Flajolet and Noy in 1998, and that is the butterfly decomposition of non-crossing trees. So what we mean by a butterfly is an ordered pair of non-crossing trees which share a root. And each of these trees that share a root will be referred to as a wing. So we can talk of a left wing and a right wing. So for the left wing is if all the vertices are less than the vertex k, which is the root of the butterfly, and it is going to be in the right wing if all the vertices are greater than k. So we can now generalize this definition and define the structure we are going to enumerate, and that is a d-dimensional plane tree, which we define as an uncrossing tree in which each butterfly is rooted at any non-root vertex as one left wing, labeled 1, and then there are d minus 1 right wings, labeled 2 all the way up to d. And we note that the butterfly rooted at the root of the tree is always considered as the right wing, labeled d. So we chose the name d-dimensional plane tree because this tree can be considered as a plane tree, and in which the d wings are in the d directions of the d-dimensional space. So the wings, as I've said, are labeled from left to right. That is 1, 2, all the way up to d. So, and all the children of the root are labeled using the label of their wing. So we can talk of the ith wing of a butterfly rooted as v. It's a d-dimensional plane tree that comprises of vertex v and all the subtrees rooted at the children of v, which are labeled I. Then we can also define a boundary edge in a d-dimensional plane tree. This is also the edge of the form 1n. That is, if there is an edge from vertex 1 to vertex n, or if there is an edge from vertex I to vertex I plus 1, where again I ranges from 1 to n minus 1. So consider this tree. So what we have here is a three-dimensional plane tree on 12 vertices. So all the vertices which are adjacent to vertex 1 are all labeled 3. That is, d is equals to 3 for that case. And if the one rooted at vertex 6, that's that vertex 6 is in the third wing, that it is in the wing even number 3. So there are 3 wings here. That's the ones in the wing labeled 1, the ones labeled 2, and labeled 3. And then we can also talk of the boundary edges. Like in this case, 12, 11 is a boundary edge, 2, 3 is a boundary edge, 3, 4 is a boundary edge. Okay, so what does this mean? So this means that a one-dimensional plane tree is just the ordinary plane tree, which you said are counted by the Catalan numbers. And the two-dimensional plane trees are just the ordinary non-crossing trees, because all the children of the root are labeled 2, and other children, the children of the non-root vertices, are labeled 1 or 2, such that vertices labeled 1 are considered to be in the left wing, and the one labeled 2 are in the right wing. Then we also define a d-dimensional plane forest. So this is a forest which is drawn in the plane, and as the case with the non-crossing trees, the vertices are the boundary of a circle, edges are line segments that do not cross inside the circle, but with an extra condition that each component is a d-dimensional plane tree. So what I've drawn here is a three-dimensional plane forest with 12 vertices. And here there are 3 components. The ones I've colored blue, then orange, and also red. So those are the components. Okay, so therefore this research unifies known results for plane and non-crossing trees by considering a generalization for plane and non-crossing trees. And we use generating functions to enumerate these d-dimensional plane trees, and our statistics of enumeration, number of vertices, root degree, vertices of a given type, number of leaves. We also use endpoints, boundary edges, forest distance, and lastly, we'll do our degree sequence. So, so the Lagrange inversion formula is key to obtain our closed formulas. So most of us, or if not all of us, know the Lagrange inversion formula. So I want to start with the root degree. So that's the root degree and vertices of a given type. So this formula stated here gives the number of d-dimensional plane trees on n vertices. If root is labeled if root has degree r, and then there are a total of ai vertices, which are not adjacent to the root, which belong to the ith root. Ith wing of the butterfly is rooted at the vertices of the trees. As usual, also here I ranges between 1 to d. So how do we construct the proof for this? So we use generating functions, as I've said. So we let t and b be the generating functions for the d-dimensional plane trees and their forests, respectively, where x here marks a vertex. Then we can say that t is given by, so it is a collection of butterflies. So that's why it is x over 1 minus b. And then how do you create a butterfly? So for a butterfly, you need to bring trees together. That's why it is t raised to power d, but we have to divide by x raised to power d minus 1 so that we don't overcount the vertices. You bring the trees together, you are gluing the vertices together. You pick from different d trees. Then there are a vertex. A vertex is from each tree is glued together. Then it means that we need to divide by x d minus 1 so that we don't overcount the vertices. And so b, which is the butterfly, is going to be given by x over 1 minus b. That's just by rearranging that. So we can let ui to mark a vertex, not adjacent to the root, in the ith wing of the butterfly in a d-dimensional plane tree. Then b, which is the butterfly, is going to be given by a sequence of butterflies. So that's why it is x over 1 minus u1b all the way to 1 minus udb. And also we know that t, which is the generating function for the trees, is going to be x over 1 minus vb. So v here marks the root degree. So t, note that t is a tree and it's formed by a sequence of butterflies. So there are going to be v butterflies if the root is it's going to be k butterflies if the root is if the root has degree k. So that's why we have the generating function as t equals to x over 1 minus vb. So what remains is just to extract the coefficient of x raised to power n vr u1 a1 all the way to ud ad in t, which we do. We now proceed to do. So how do we do that? We use we know that t is how t is expressed. That is x over 1 minus vb. So that's what we have there, which we all know that if you have 1 over 1 minus vb, you can write as the sum of v to power k, b to power k, and you sum over all the k's. So then taking the coefficient of v to power r, we get that that's the same as getting the coefficient of b raised to power r. Coefficient of x raised to power n minus 1, u1, a1, all the way to ud, ad in b raised to power r. So we just use the Lagrange inversion formula to get the required formula. So there are corollaries that follow from that. One of them is when the root degree is r, but then you want to get the total number of such trees on n vertices, which is given by equation 1. So it follows by just extracting the coefficient of x raised to power n vr in t, which is done as follows. So we know what t is, that is x over 1 minus vb. And then as we've done before, this is going to be the same as the coefficient of x raised to power n minus 1 in br. So we use Lagrange inversion formula at that point, then to get our result. Then when we set d equals to 1 and d equals to 2, then we discover the formulas for the number of entries on n vertices with root degree r, which was first obtained by the Chavez and Zaks 1980. And then we take d equals to 2, we get the number of uncrossing trees on n vertices with the root degree r that was obtained by Noy in 1998. So then we can get a number of such trees with a given root degree and vertices of a given type. That is, if there are AI vertices in the earth wing of the butterflies rooted at vertices of the tree, where A ranges from 1 to D, then the number of such D-dimensional trees on vertices is given by equation 2. So this follows easily from the theorem we just proved by noting that we only need to take R that is in here, we just need to take R and AD, sum of R and AD to AD. Then we obtain the formula 2. And then number of non-crossing trees on vertices with I vertices, in which there are I vertices in the right wing of the butterflies, is given by this equation here. How do we obtain this? So here A2, so because it's non-crossing trees, so D is 2, so A2 is I, because it's in the right wing. And then A1 is going to be N minus I. So by doing that substitution in 2, we get this formula here. So this formula, this result I noted before. Then the total number of d-dimensional trees on vertices is given by a generalized form of scalar numbers, that is given by 3. So how do you obtain that? We extract the coefficient of Fn in the generation function t of x, which is done here by means of the Lagrange version formula. Then you get the equation 3. So you also note that the formulas that we had stated before for the plane trees and non-crossing trees are just obtained easily from 3 by substituting d equals to 1 and d equals to 2. Okay, so other parameter we want to look at is leaves. The leaf, I said, this a vertex without degree 0. So the number of d-dimensional plane trees on n vertices with root degree r and having n leaves is given by equation 4. So we construct the proof as follows. So we let T and B be trivariate generating functions for d-dimensional plane trees and butterflies, and here x is going to mark a vertex, u marks a leaf, and v is going to mark root degree. Then the generating function for the trees is given as x over 1 minus vb, as I explained before. But for the butterflies, it's going to be that was there for the butterfly, but because we want to introduce the leaves, so we have xu, that's where u is marking a leaf, but because we don't want to count the vertices, then we subtract x. So then we can write b as follows by substituting what t is, and then the formula is obtained from this by just the application of Lagrange inversion formula. And when we sum over all r, that is in this formula here, we sum over all r with the root degree, then we should get the total number of the trees with n vertices and n leaves, which is given by equation 5. So other results that we obtain that are found easily from this result. So one of them is when you set d equals 1. So if you set d equals to 1 here and use an identity that you have negative n choose I times negative 1 raised to power I, then you should get n plus I minus n minus plus I minus 1 choose I, then you get this result here. For the number of plane trees on n vertices with leaves, which was obtained by Maseno and Axos in 1980. Formerly, I may always refer to as an area number. Then when we set d equals to 2, then we get the number of non-crossing trees with n vertices with leaves. That was also obtained by Flajolet and Noy. Then we can talk of endpoints. Also, you remember endpoints, we said these are vertices with degree 1. So the number of those non-crossing d-dimensional entries on n vertices with L endpoints is given by equation 6. Where N, L, S, and L and U and L are as given here. So how do we construct that proof? We know that trees on n vertices with n leaves are either d-dimensional plane trees on n vertices with root degree greater than 1 and having n leaves, or they can have root degree 1 and then L minus 1 leaves. So we need to get these trees with n vertices, n leaves, and having root degree greater than 1, that is obtained by T and L minus S and L. But then, and then the ones with the root degree 1 and L leaves is given, the root degree 1 and L minus 1 leaves is given by U and L. And then that completes the proof. So we can obtain, for the boundary edges, the number of d-dimensional plane trees on vertices with the L boundary edges is given by 7, which is the same formula, which was counting 1 for the endpoints. So the endpoints and boundary edges, the number of those trees are the same. And the proof just followed by just adapting the proof given by Dosh and Noy. So the construction is the same. So we can get, by summing all i's, then we can obtain the number of plane trees on n vertices and n leaves or boundary edges as given by this formula here. Moreover, when we take d equals to 2, then we obtain the number of boundary edges and crossing trees. That was also given by Dosh and Noy. Then the other parameter is forest. So forest, we say this is a collection of trees. d-dimensional plane trees. So the number of d-dimensional plane forests on n vertices with k components is given by 8. So let's see how to construct the proof. So we'll let t of x and b of x be the generating functions for d-dimensional plane trees and butterflies, where x are mass vertex. Then, as we have done before, they are expressed as 9. Then we can let f to be a forest and v be the number of vertices in the component C containing vertex 1. So to obtain f, which is a forest, there are v additional forests in the spaces constructed, between consecutive vertices of C. That is expressed here. So if you want, so you start with the tree, put at vertex 1, this tree. So between those two vertices, between the vertices of the trees, there are forests which will possibly be empty. So a family of forests therefore can be obtained from family of trees by substituting a vertex in the tree by a pair, that is a vertex and a forest. So if f xw is the bivariate generating function for d-dimensional plane forest, where x marks a vertex and w marks a component, then by the construction, we have that f x of w can be expressed as is either empty, that is 1, or they are w marking the component, so it's w times t of x f. It is because a vertex is replaced by a pair, which is a vertex represented by x and a forest represented by f. So from the generating functions for a tree and the butterflies, we get that t, which is t of xf, will be expressed as in 11, and b will also be expressed as shown, so that we have that xf is expressed as 12. So we bring everything together and find that f, which is the generating function for the forest, is just 1 plus wb times 1 minus b minus 1. And for the butterflies, is given in 14. So we extract the coefficient of Sn because n was the number of vertices and x was marking a vertex, and w to per k because w was marking the components and the are k components. So we do that extraction, and with the help of the Lagrange inversion formula, then we get the formula for the vertex. So we can get that number of d-dimensional plane forests on n vertices is going to be given by taking the sum of all the components. Sum of the formula, you sum over the components. Then we obtain the number of forests, plane forests, and plane crossing trees by setting d equals 1 and equal to 2 in formula we just obtained. So we find them. So these are results that have been obtained before. Then for the distance, so there are this number of d-dimensional plane trees with n vertices, of which there are k distances. So how do we prove that? Again, we let xz to be the bivariate generating function for d-dimensional plane forests, where x marks areas and z marks a distance. Then we also let t tilde to be the analogous generating function for d-dimensional plane forests, where here the root is not vertex 1, but it's a vertex with highest number. Then we'll express 16. We'll express d of z as shown in 16. And this is because each butterfly, the root has one number than the vertices in the dimensional wings, but a higher number than in vertices in the rightmost wing. Then the same applies for tilde, t tilde, that is 17, and here all root vertices are different. So that's why it's expressed in that as expressed in 17. So if we limit t tilde in 16 and 17, then we get 18. That 18 is not before we can apply a Lagrange inversion formula. So we set t to be equal to 1 plus s. So then that equation 18 becomes this in terms of s. Then just apply the Lagrange inversion formula. Then we get the formula for the number of dimensional plane forests with n vertices and give the number of digits. Then when we set d equals to 2, then we obtain the results that we obtained by David House, and this was giving the number of crossing trees with n vertices with a digits. Then for the d-dimensional increasing d-dimensional plane trees, we need to set k equals to 0, that is d equals to 1 here and k equals to 0. Then we get the number of increasing d-dimensional plane trees. That is, we only set k equals to 0 because the total of increasing, so there are no descents. Okay, then lastly, for the degree sequence, we find that the number of d-dimensional plane trees on n vertices with d vertices how degree k is given by this formula here. And how do you construct the proof? Is what you do, you let v be the vertex of degree k in the tree, and then in that tree, maximum degree is r. Then there's going to be a sequence of k butterflies attached at vertex v. Then these butterflies are to be distributed among d wings. And this is the same as choosing k objects from a set with d elements, such that repetition is allowed. So simple combinatorics shows that the number of such trees is given. The number of such ways of doing that is d plus 1 plus a minus 1 plus a. So the generating function for the butterflies is given as shown, and then if we let wi to make a vertex of how degree I, either in trees or the butterflies, Then B is expressed as A20, and the equation for the butterflies is therefore given as the sum as X times the sum of WI, and we sum over all the I's. And therefore we use 20 together with the expression for T and the graph inversion formula to arrive at the result. So in this work, we have unified various results for plane and crossing trees. That is, we have considered root degree, vertices for a given type, leaf, endpoints, boundary areas, presence, and out degree sequences as the statistics of enumeration. So there are various projections that have been constructed for plane trees and non-crossing trees, like plane trees with hypers, plane trees with the binary trees, or non-crossing trees with the ternary trees, non-crossing trees with the structured lattice paths, etc. So I hope that this work, that those projections can also be generalized by considering d-dimensional plane folds, plane trees. So here are some of the references we've been talking about. I want to thank all of you for listening to me. I want to thank for Maseno University for producing the environment to conduct this research. And as we say, it's widely Sasa. Thank you very much.
Thank you very much, Dr. Isaac, for this insightful presentation on generalized entries. And now we open the floor for questions and comments from the audience.